This is the first video for chapter 17 in the McGraw-Hill chemistry text, and this time put it all into one video, so maybe just a tad longer, but there's just one video and one page of notes. You should have the page of notes. If you don't have that downloaded, it'd be a good idea. It's just a little hard sometimes to see on the big screen here. So chapter 17 is about chemical equilibrium and solubility product constants. Really, there's going to be probably almost half of the chapter will be problems, but there's going to be two main categories, so it's a little easier in this chapter than it might be in other places, in other chapters. We're going to have our equilibrium constant problems and our solubility product constant. So that may not make a lot of sense to you now, but hopefully when you're done, it will. So we're going to look at the chemical equilibrium first. So when we have chemical equilibrium, we're going to use this tank. I think it's a good example for you to think about equilibrium. I've got water in this tank. You can see that it's moving back and forth here. And once I let it sit, the tank will be in equilibrium basically. Now, does that mean that it's not moving any? No, it's a dynamic equilibrium. There's water that's kind of wandering across this way, but there's also one wandering that way every time, because if you had more wandering one way, the water would pile up on one side. You know that doesn't happen. So that's what equilibrium is. Now, equilibrium right now is 50-50 here. That's not really what it always is. Matter of fact, it's usually something other than 50-50. So here I've tilted it up a little bit, and you can see that I've got a P on this side and an R here. That stands for products, that stands for reactants, just for a generic equation. You can see that there's more product than reactant right now. So we say that as product is favored. There's more product. And that's still an equilibrium. It's not 50-50, but there's as much going left as there is going right, and it's kind of leveling out and staying equilibrium. The law of equilibrium is actually just the way that we set up the equilibrium equations. And here on the next page, you see the law of equilibrium down here. Basically just says that when little a, big A, plus little b, big B, that little, just like we used in last chapter, the little letter stands for the coefficient. So the little letter is a number, whole number. The big letter is the stuff, like H2 or H2O. So it's a compound. And we've got A plus B yields C plus D, but it's a two-way arrow. And, you know, sometimes there may not be two reactants. And sometimes there may not be two products. But, you know, it's there in case you need it. And you can see that K, which is often used, capital K, or KEQ or KC, they're all used to equilibrium constant, is equal to the product of the products, in brackets, over the reactants. Now, if there's more than one, they're multiplied. Make sure that you make a note that they're multiplied, because on the test and quiz, a lot of times I'll have people calculate and they'll put pluses in there, and you're going to get the wrong value if you add instead of multiply. Now, just like in last chapter, the coefficient, the number in front of the chemical, goes to the power of the brackets. So you can see here, the little a is the power, the little b is the power. It was the coefficient over there. And again, products over reactants. Now, this is really important up here where it says if KEQ is greater than 1, that means that if it's like 2 or 5 or 800 greater than 1, then products are favored. And that should make sense to you. Look what's on top. The numerator has the products. And what you learned back in maybe 3rd or 4th grade when you start dealing with fractions, if the number on top is bigger, it's greater than 1. The number on bottom is bigger, like 1 over 2. 2 is bigger. 1/2. It's less than 1. And you need to know that, because I will ask you on the quiz and the test, are products favored? Are reactants favored? You're going to solve for KEQ, and you should be able to tell me that. When products and reactants are present in more than one state, we call this heterogeneous equilibrium. We're going to talk more about that later. For now, we're going to generally deal with the homogeneous equilibrium, which means they're all in the same state. And it has mostly to do with pressure. The gases are affected by pressure, solids and liquids are not. Should be able to write KEQ expressions and solve for KEQ values if you're given the numbers. So we're next going to talk about Le Chatillier's principle, and this is a kind of a big part of the chapter, and for a lot of people it takes like pages and pages to do, but you know, I've always learned that when we're trying to teach something, if the concept can be taught as one thing and just compare everything to that one thing, it's a lot easier. That's what we do here. So we're going to compare it to this tank again, and in class I use a big aquarium, so it's probably a little easier to see and a little easier, maybe makes a little more, I don't know, maybe makes it a little more visible to you, but it should still make sense here. So the idea here is this is an equilibrium, but we could do things to the system, you know, kind of like somebody next to you, you could bump them or shove them and you're going to cause something to happen. Same thing with this system. If we add some to the reactants or add some to the products, it's going to cause, now we're using an analogy here, if I add some water to this side, the water is going to flow this way, right? If I add some water here, it's going to flow that way. It doesn't just pile up where I add it. It flows until it's level on top again. And that's exactly how all of Le Chatillier's principle works if we could compare it to the aquarium. Okay? So let's think about adding reactant. So I'm going to scoop a little out here, and then we're going to let that kind of stabilize, let the waves go down. So I've got some water here. If I add water on this side of the aquarium, what happens to the overall movement of water inside? Of course, the water goes towards the other side. And the reason for that is that it's not just going to pile up here where I put it in, it's going to level out. And it has to flow the other way to level out. It's the same thing with Le Chatillier's principle for reactants. If I add reactants to the reaction, it goes to the product side. And the way you state that is you say it reacts or moves to the product side. Or you could say to the right. If we add product, then it moves to the reactants. So the side you add, just like in this aquarium, when we add water here, it moves that way so it can level out. If we add water here, it moves that way. If we add reactants in a reaction, then it causes the reaction to move more towards products or favor products more. If we add product, it moves more towards reactant. Now, what about taking stuff away? Well, if I scoop out here, it's not just going to stay with a little hole there, it's going to fill. So it comes from the other side to fill. So it's kind of the opposite of adding. If I take out from product side, then it shifts from reactant to fill where I just scooped, where I took it out. So if I take out products, then the reaction shifts to fill on towards products. If I take out reactants, then it shifts from products to reactants to fill that hole. It's the same with the reactions. So remember, reactants and products, if you add a reactant, it shifts to products. You add a product, it shifts to reactants. If we take away a reactant, it shifts to fill where we took things away. If you take away products, it shifts to products to fill. Okay, so cooling and heating. Now, to do that, we need an equation that has heat. So I'm going to make an exothermic here, and I'm going to add an H here for heat. Okay, so we've got a little H there, and it's kind of hard to see probably, but we've added the H on the product side. And it's all important what side the H or heat is on. Now, instead of the heat, instead of writing heat, I may give you a amount of kilojoules or amount of kilocalories. That's what you're looking for. The word heat, kilojoules, kilocalories, look at that side because it's going to be just like what we just talked about. Okay? We're going to be adding chemical, we're going to be adding heat. The heat adds to the whole system, but it actually adds to the side with the heat. So where the H is, that's where the heat is. If I add heat to the whole system, it doesn't affect this side over here. it adds to the side with the heat. So it's just like another reactant or product. In this case, a product. If I add heat to the whole system, it adds on the side with heat and shifts to reactants. If I take away heat, then it removes from the heat side. So what are we doing when we take away heat? We're cooling. So if I cool this whole system, then it takes away on the side with the heat and fills just like the other concepts we talked about earlier. So remember that if heat is there, if it's on the product side, then treat it like it was adding a product. If it's on the reactant side, then it's an endothermic reaction. Treat it as though you're adding on the reactant side or taking away on the reactant side if you cool. That's heating and cooling. Finally is pressure. So probably best to think of a reaction. The one I use in class is the hydrogen balloon that we blow up in the beginning of the year. H2, 2H2 plus O2 yields water. So water is our product, and 2H2 and O2 are reactants. For pressure, remember we pressurize the whole system. So it's not like we just pressurize the reactants or just pressurize the products, but we pressurize the whole system. The place it affects is the side with the most moles of gas. So for that reaction we talked about with 2H2 plus 1O2, that's the gas, produces 2H2O. We'll call this a gas, it doesn't really matter. There's 2 moles of hydrogen gas, 1 mole of oxygen gas, for a total of 3. So when we add pressure, it adds to the side with the most moles of gas and shifts to the product. If we take away pressure, it takes away from the side with the most moles because there's more moles of gas to be affected. So that's the whole package with Le Chatillier's principle. If you need help with it, come in. We'll go over it. Come in tutorials. So now we're going to shift gears and talk about the other side of the chapter, which is KSP, or solubility product constant. When we talk about solubility product constant, this deals with a chart that you're going to have on your possibly useful page. I'll show you a picture of it. This is the actual possibly useful page right here. And the chart is up at the top. So, when we do this, if you need to, you can kind of run back to this screen and look at your chart and get the values. But there's also a chart in your book. So either get a book out, or you could possibly download the chapter and have it on down on the toolbar, so you could pop that up, pause, and pop that up. So what is the KSP chart? When you have partially soluble, slightly soluble salts, there's a limit to how much you could put in solution. Kind of like lifting weights. You have a limit, we call it your max. That's the most you can lift. Well, this is the most that the solution can hold. And we call it our solubility product constant. So the solubility product constant is when we multiply the ions, the 2 types of ions, then the product of that is what's listed on that chart. So we'll be looking up the chart. We'll be looking up values on the chart to find out what's the total amount that those ions that can be dissolved in a solution. So the KSP solubility product constant, when you write these, the first thing you write, just like with the KEQs that you write, the first thing you write there is KEQ equals. This is the KSP equals. So the solubility product constant equals, and it's going to be the product of the products. What is a product? When you multiply, you get a product. That's how it's easy to remember. So first step of doing this before you even write it is you need to dissociate the salt that you're dealing with. So let's say, like we've got here on the screen, let's say that we're dealing with lead chloride. That would be PbCl2, lead 2 chloride. So we're going to dissociate that, and when we dissociate it, we get Pb2 plus 2Cl minus. There's 2 chlorines, and so basically we've got Pb with Cl and Cl attached. When it breaks apart, there's 2 chlorines and 1 lead. The KSP will be written KSP equals, and then you put the number of brackets equal to the number of parts, and then in 1 we'll put the Pb2 plus raised to the 1 power because there's a 1 in front. There's a 2 in front here, so we'll put Cl minus raised to the 2nd power. So that is our KSP expression. A lot of stuff similar to what we did with KEQ and what we did in the last chapter with rate laws. The power comes from the coefficient. So now that you've written that, we're going to talk about the 3 types of problems that you'll see. Remember that KSP chart's on page 615, and you might need a copy of that to refer to it. So we're going to talk about calculating a basic KSP. The basic KSP problem, you will get a simple salt like AgCl when the coefficients or when the power here is plus 1, the charge, and minus 1. When the charges are the same, it's the simplest problem because we're just basically going to be taking the square root of the KSP that we look up. So here is AgCl splits into Ag plus Cl minus. KSP, remember we do the equal to the number of brackets that we have of products. We have Ag plus and Cl minus, and we now we're going to solve for one of them. Doesn't matter because they're equal. How do we know they're equal? Well, AgCl, when it's together, is like the pin in the cap. When it breaks apart, for every cap, you have a pin. So we know those 2 are equal. And that'll help us because if we're solving for silver and we know that Ag concentration equals the Cl concentration, then we can substitute and get rid of one of our unknowns. Something important to remember now and in physics. 2 unknowns, 2 equations. Here's our other equation. Ag equals Cl. So we're going to substitute, instead of Cl, we're going to put in Ag. Now we've got rid of our unknown, and we've got one unknown, Ag. So we'll say Ag times Ag is Ag squared, Ag concentration squared. So now all we got to do is look up our concentration, our KSP, and the square root of the KSP, square root of Ag squared equals Ag. So our answer to what's the silver concentration, that's just the square root of the KSP. So if we look up silver chloride, which is what we have here, AgCl is 8.5 times 10 to the negative 12. Nope, no it's not. It's 1.8 times 10 to the negative 10. So 1.8 times 10 to the negative 10. That would be the square root of that is your answer. Look on your calculator. Make sure you're familiar with where the square root key is. For the Casio, it's shift x squared, and you can see the little radicand right up above. So we would enter for this one 1.8 exp to the 10th, and then hit the plus minus, and then we hit the shift and square root. It's 1.3 times 10 to the negative 5th. And we've got 2 significant digits, 1.3 times 10 to the negative 5th. Molarity is the Ag concentration. It's also the Cl concentration. They're equal. So that's the first type of problem. Now really along the same lines would be a little bit more complicated math-wise, but it's still the same basic idea, and that is when we have a situation where the charges are not the same. Here we have a -1 and a +2. We're going to have a 1 and a 2, which means that Pb is 2 plus and plus Cl is 1 minus, but there's 2 Cl's. Because there's 2 Cl's, that means when we write the KSP equals the Pb2 plus concentration times the Cl concentration squared. There's another factor you need to consider, though. There's 2 Cl's for every Pb. So we're going to say Pb is X, right? One of those. How many Cl's are there if there's 1 of these for every 2 of these? Well, this will be 2x. So we have the KSP equal to x times 2x squared. 2x times 2x, well, 2 times 2 is 4. X times x is x squared. That's 4x squared times x, 4x cubed. 4x cubed. So a little bit more difficult algebraically. We look up KSP. So let's say for PbCl2, PbCl2 is 1.7 times 10 to the 5th, negative 5th. So we're going to divide both sides by 4 and get rid of this 4. Okay, divide both sides, or Anderson swap the 4 down. And now we've got this value equal to x cubed. We don't want x cubed, we want x. So let's do the cubed root of x cubed, which equals x. And the cubed root, we have to cube root both sides of this. So we do 1.7 exp 5 to the plus minus divided by 4. Don't forget to hit the equal. If you don't hit the equal, you're going to be taking the cube root of 4. So equals, you'll get that value. And then the cube root key for the Casio is right above the plus minus. So it's shift plus minus. Right over here on the left, kind of third row down, left. Shift, and then the plus minus key. On your other calculator, I don't have one handy here, but do make sure that the calculator you're using, you find that cube root key, because you'll need to use that cube root key. So you basically get the value, divide by 4, hit equal, and then you do shift cube root, you get your answer. That's the same type of problem, but a little bit tougher because it's got the cube root instead of square root. All right, 2 more types of problems and we're done. The next type of problem is the precipitate. When you see a precipitate problem, it's a KSP problem. So here we have a precipitate problem. Let's see if we've got an example we could put up here. No, we don't, but let's say we've got a AgCl. We've dealt with that already. So we've got Ag plus Cl minus, and KSP is going to be it's going to equal the Ag plus times the Cl minus. And then now you've got your KSP. We're going to change this to something we call QSP. We're going to go into the problem and we're going to find the silver and the chlorine that we're adding. Usually it's going to be 2 solutions. And we're going to find out, does that value exceed the KSP? So we're going to solve for the solubility of the actual question. We call it QSP. And we're going to check to see if it's greater than KSP. Think about an 8-ounce cup. If you try to put 6 ounces in an 8-ounce cup, no problem, it fits. If you try to put 10 ounces in, it overflows. That's kind of what the KSP chart tells us. It tells us the capacity, what it can hold in ions for slightly soluble salts before it precipitates out. So the QSP is what we're solving for here. Let's say in this problem that we add some AgNO3, and let's say we're adding a liter of total solution, and we have 0.001 moles of AgNO3, silver nitrate. Okay, so just like when you get coffee, talking about coffee a lot in today's lesson, the coffee is what's important, but you need the cup to carry it or to hold it. when you get through with the coffee, throw the cup away. It's not important to us, or you recycle it. Well, it's the same here. We're not worried about the NO3. There's no NO3 in our precipitate problem. It's the Ag that we're worried about. And again, like the pen and cap before, if we have 0.001 moles of AgNO3, we have 0.001 moles of Ag and 0.001 moles of NO3. But we don't care about the NO3. So we're going to put 0.001 in here. And remember, the brackets mean moles per liter, or molarity. So we don't need to add a unit. And then let's say to that we add 0.002 NaCl. Okay? Not worried about the Na. We're worried about the Cl. 0.002 of NaCl has 0.002 Cl concentration. Now we multiply these. So we've got 2 times 1, which is 2, and we've got 1, 2, 3, 4, 5, 6, so times 10 to the negative 6. Well, let's go look at AgCl and see what the value is. For AgCl, it's 1.8 times 10 to the negative 10. So the KSP is 1.8 times 10 to the negative 10th molarity squared. Now, right away, you'd say, oh, well, 10 to the negative 6th is smaller, but it's not. Remember, it's a negative exponent. So the negative 6 means 5 zeros in your number. The negative 10th means 9 zeros. So that is smaller. We've exceeded that value with our QSP. There will be a precipitate. That's how you decide if there's a precipitate. Okay? So, lots of practice problems on that. There's some on your review too. We'll finish up talking about common ion product. So, if you get a problem that has 2 solutions and they're added together, they will give you the molarity of one solution. They'll give you a saturated solution for the other. And it could be 2 saturated solutions, but you already know how to solve for a saturated solution. When you see the word saturated solution, you know to go look at your possibly useful chart right up here on the top, that KSP chart. So let's say that we're going to work through one I think we have on the review. They tell you have 0.020 molar AgNO3. Okay? They just tell you that. That's solution 2. Okay? We're going to start with solution 2 because it's easiest. We don't care about the NO3, so we know already in that we're adding 0.020 moles per liter of silver. Done. Okay? Let's look at the other solution. Now, in the other solution, they're going to tell you that we're adding, trying to remember what the one in the book was. I think it was AgI. So they told you that they had a saturated solution of AgI. Well, how do we figure a saturated solution? We look up the KSP, which is equal to 8.5 times 10 to the negative 17th molarity squared. Well, how did we do our saturated solution earlier? Remember all the stuff we went through? We ended up just taking the square root of it. Well, that's what we're going to do here. So KSP is equal to Ag times I. And we know Ag and I are equal because of the pen and the cap, right? AgI splits. The Ag and the I are going to be, one cap, one pen. So they're equal. So we know that we can substitute in Ag. That's Ag times Ag, which is Ag squared. Take the square root of that, square root of this. When you take the square root of a power of 10, it just cuts it in half. The answer to the square root will be, in this case, 10 to the negative 9. Can't do 8.5. So 8.5 rounds to 9 whenever this is over 5. And so 9 times 9, it's going to be 0.000000092 because 92 times 92 gives us 8.5. So you do it on your calculator. It's easier. So we're going to take the square root of 8.5 times 10 to the negative 17th, enter the value, hit the square root key, and you get 0.0000000012345678992. This is where these problems can be really easy because the second source is going to drop off the map. Remember significant digits? In addition, we don't have values beyond the thousands. All of this stuff goes away. So what's our value for silver? 0.020 molar Ag. That's it. It was our second solution. The first solution source was so small it went away. Can we predict that? You can look at the square root and take 10 to the half of the, whatever the negative power, 10 to the negative of one half of that, and you can figure out how many zeros that is. It may drop off the map. I'd like for you to show the work anyways. You got your calculator, punch it, do it, add them up. Now, here's the last step. The silver quantity, the 0.020, now we write a KSP equals 8.5 times 10 to the negative 17th molarity squared equals Ag times I, and we're solving for the I. We've got that number, and now we have the silver, 0.020. Well, all we have to do is simplify and solve for I. The KSP value, we're going to Anderson swap the 0.020 down, or you could divide both sides by 0.020. I've showed you it's the same thing. And you're going to end up with 8.5 times 10 to the negative 17th divided by 0.020. That's the iodine concentration. That's how you always figure out the final concentration. Because remember, the concentration of silver times iodine multiplied together can't exceed that amount at that temperature. So it's kind of like a seesaw. If one of the amounts is real big, the other one's got to be real small, because when you multiply them, it can't exceed that KSP value. So that is how you solve common ion products. There are some common ion product practice in your notes, also in your practice pages. There's 2 sets of practice pages. Also, you've got some on your review. Work your review, come in for tutorials. Good luck.